So I would just like to rework on this problem again to illustrate again how buffer resists pH changes. Let's say, for example, if you're adding a strong acid HCl into strong base KOH, the pH will drastically change. Whereas if you add the strong acid hydrochloric acid to a buffer, the pH will actually barely move or barely change. Okay, let's see the first case. So for the first case, you have 1 ml of 2 molar KOH. So um, what we see here will be the hydroxide from KOH should react with H plus with a proton from HCl. Okay, so again, they will not form a buffer. So this is not a buffer. But let's figure out how the pH changes. Okay, but first initially, okay. So to determine the pH of this solution before we add HCl, so remember that pOH is equal to negative log of 2 molar. Okay, 2 molar here, remember, is the concentration of OH as well. Okay, so from that, we're going to get negative 0.30, okay, which just means you have a pH of 14 minus negative 0.30. It's equal to 14.30. Good. Okay. And then next, now that we know the pH originally, let's actually do an ICF table, figure out how much of the strong acid is consumed by the strong base. Okay, so let's say, for example, so to write an ICF table, we have to consider, let's look at their millimoles. So we have H plus from HCl reacting with OH from the KOH, producing water. Okay. Then to calculate for number of moles or number of millimoles for H plus, so we are given 0.50 ml. No need to convert again if we're working with millimoles. Okay, 0.50 ml times 2.00 molar. That's the concentration of H plus as well. So that's going to give you 1 millimolar. Okay, and then for hydroxide, that will be 1 ml times 2.00 molar. This will give you 2 millimolar. Okay. Okay, and then for water, we just assume that there's none of it to begin with. Okay, now so you can see here H plus is the limiting reagent, so that will fully be consumed. Okay, and then it will form that amount of water, but we don't really care about water. So this is 0, and then this one will be 1.0, then this will be 1.0 again, but also we don't care about water again. So as you can see, after you mix the two of them together, the acid will be fully consumed by the base. And again, just because I erased it already, originally the pH here was 14.30. Okay, so this is the concentration of OH that we have now. So let's calculate what the pOH is. So the negative log, or sorry, pOH is equal to the negative log of the OH concentration. We have here 1 millimole. Okay, 1 millimole divided by, now the total volume of the solution is 1 plus 0.50. So that's 1.50 ml. Okay. Keep in mind, by the way, I'd just like to talk about millimoles again. And how, if we're not yet convinced, because when I was an undergrad, I wasn't so convinced as well. How millimoles divided by ml will actually lead you into molarity as well. So keep in mind that this thing, I can actually rewrite that as 1 times 10 to the negative 3 moles. Okay, that's the prefix milli, after all, divided by 1.50 times 10 to the negative 3 liters. Okay, So here, times 10 to the negative 3 will just cancel out. Okay, and in the end, what you will just get will be moles per liter, which is the unit for molarity. Okay, but again, that's just what I need to convince you. Okay, I find millimoles convenient. So this should give you equal to negative log of 0.667, which is just POH of 0.40. Okay, and then finally the pH therefore should be 14 rather, 0.0 minus 0.40, and that will give you 13.60. So the drop in pH from this value to this value, okay, is actually 0.70. In terms of pH, it's actually a large drop. Okay, so how about if we add that amount of HCl to a buffer? Okay, so if we add it to an ammonium bromide buffer, HCl or the proton will actually react with ammonia because ammonia is the base. It will not react with ammonium ions because they're both acidic. Okay, so let's first write an ICF table when that happens. But actually before that, you know what? Let's actually calculate for initial conditions first. Okay, so the initial conditions will be basically this. Okay, and I'm just gonna use the next slide to work on that. But the initial conditions will be pH is equal to, you're given the Kb of ammonia. Okay, so you want the Ka of ammonium. So that will just be negative log of, well, we need to find first what Ka is. So 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So basically, this is calculated for Ka. And if we get the negative log, then that's pKa. Okay. Then after that, that would be plus. We're given the molarity values. Okay. Plus log of 1.00 molar divided by 0.8. Let's see how many sig figs it has. 0 molar, 2 sig figs. Okay. And this will just give you 9.26 plus 0.10. Okay, I think we can use this pKa value later. Okay, so let's just put a note here that this is pKa. Okay, so that our calculations later are simpler. Okay, and then when we calculate this, this will be 9.36. So that's the original pH. Okay, so back to what I was saying earlier. The added hydrochloric acid will react with ammonia to produce more ammonium ions. Okay, so let's write an ICF table for that. So that's millimoles, and then H plus from hydrochloric acid, and then we have ammonia plus ammonia, which will give you H4 plus ammonium ions, more ammonium ions. Okay, we have actually already calculated earlier the number of millimoles of H plus, that's 1. Okay, now for ammonia, we have here 1 molar and you have a 500 ml solution, so that should be 500 point, how many sig figs are there? Well, there's none. So ml times 1.0 molar. Okay, so this one will just be 500 millimoles. Okay, and then for ammonium, we can get that from the concentration of, well, it's actually provided. Okay, so that will be 0.8 times 500. Okay, so that's 500 ml times 0.80 molar. It's actually equal to 400 millimoles. Okay, obviously here H plus is the limiting reagent, so minus 1 plus 1, this will be 0, 499, and this will be 401. Okay, and then if we calculate for pH, We've done this in class before, but I just want to rehash this again. So pH is equal to pKa plus log of the concentration of base over acid. Okay, but we know what pKa is already, so that's pH is equal to 9.26. Okay, just don't want to calculate that anymore. I'm not sure about you. 9.26 plus log again of the concentration of base over acid. So that's just going to be the concentration of the base is 499 millimoles divided by, now we have a total of 501 ml of solution. Okay, and then all over, oops, 401 millimoles divided by 501 ml. And again, milliliter, 500 milliliters conveniently cancels out. Millimoles also cancels out. So we're just left with the log of 499 over 401. Okay? The pH therefore should be equal to 9.26 plus 0.09. And the pH of the solution should be 9.35. So looking at these two values, notice that the change in pH is just equal to 0.01, a very tiny value.